Hi, okay, I got some echo just now, and now I think it's all good. So hello, welcome to ethics seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Medley. She's our communication specialist. Kathy and I will be today's moderator, and we are excited to have our speaker, Professor Lynne Talley, joining us from UCSD. A few things before we get started. So the seminar is being recorded and it will be later published on our YouTube channel. Please be free to ask questions. You can do so by raise your virtual hand and we will unmute you. You can also send us text message in the chat. So let me briefly introduce the speaker. So Professor Lynne Talley is a distinguished professor of physical oceanography and Scripps Institution of Oceanography, University of California, San Diego. Talley's research focuses on the general circulation of the ocean and the role of various oceanic and atmospheric conditions that affect ocean currents and property distribution, and the role of the ocean in climate. She was a lead author of the IPCC 4th and 5th Assessment Report, Working Group 1 chapters on ocean observations. Her particular emphasis over the last decade has been the Southern Ocean processes. Since the 1990s, she has been a principal investigator for global ship-based hydrography, now GO-SHIP. And in recent years, she has been a principal investigator for the NSF funded Southern Ocean Carbon and Climate Observation and Modeling, the SOCCOM program, which has built a Southern Ocean network of Biogeochemical Argo Flux. She is currently also a principal investigator for the GO-BGC Argo of biogeochemical floats, and she has authored and co-authored more than 145 publications and is lead author of a physical oceanography textbook. Let's welcome the speaker, and I will hand this over to Professor Talley. Professor, please proceed.
Okay, hey, thanks very much for inviting me, John, and hello, everybody. I'm talking to you from San Francisco, visiting family here. So I'm glad to be here today and tell you about our program and some of the findings. What you're seeing going by in blinding sort of this animation is the floats that we've been deploying over the last let me get started here. Over the last several years. So there's the title, Peppering, as if we're a salty ocean, the Southern Ocean with Biogeochemical Argo floats. And on the left, you see a picture. This is actually Barney Balch from a Bigelow lab. They were deploying some floats on the Ravel a couple months ago. We're currently deploying actually in the in the Sargasso Sea, Western North Atlantic, for the brand new GO-BGC program. So I want to just point out our website up here, SOCCOM, SOCCOM.princeton.edu. You'll see why Princeton on the next slide. I have some spectacular pictures of the Southern Ocean, which I want to credit Isabella Rosso, who's an early career scientist at Scripps, and Ted Blanco, who was an outreach person for SOCCOM. SOCCOM, which John introduced, that long title. This is our team. Jorge Sarmiento at Princeton is the lead PI and led us into writing this proposal a number of years ago. And we were successful and very happy to be successful. This is building an amazing observing system and also developing coupled climate model and state estimation for the Southern Ocean is the main goal of the program. Our associate director is Ken Johnson, MBARI. And he's basically running the program now. Jorge has been quite ill, and Ken is the real lead of these biogeochemical floats for the globe. And then there's our team, me and Steve Reiser running the observations, Joellen Russell at Arizona for modeling, And then we have state estimation, which is basically data assimilation for the Southern Ocean. That's Matt Maslow at Scripps. And then we have some broader impacts. And on the right, you'll see our additional members of the team: Oscar Schofield at Rutgers, Manuel Boss at University of Maine, Curtis Deutsch at Princeton, Bob Key at Princeton, Andrew Dixon at Scripps, and Ariane Verity for state estimation, and Sarah Gilly, who's a PI at Scripps. So I want to introduce our new team as well. Since this is a brand new program, we're just deploying our float number 6 went in the water an hour ago. We got the email. This is a program building up to 500 floats globally. We're using the Southern Ocean experience of our last 6 years to say that we are ready to do this globally. NSF agreed, and we got MSRI 2 funding from NSF to the tune of about $50 million plus operations. And for this program, which is infrastructure only, and we call it GO-BGC, Ken Johnson is the lead PI, and you'll see familiar faces there: Steve Reiser, Jorge Sarmiento, and myself. We've added Woods Hole with Susan Wafels, and there's Heidi Cullen again for outreach. So we're very excited. You see the map up there. That was this morning's map showing the first several floats that have gone in on a line south of Newfoundland, heading towards South America and back up to Woods Hole. So that's just introducing our team. I wouldn't be here without the big team. This is really very much a joint effort, and we pioneered telecons as before this year of Zooming everything. We were still on telecons 2 or 3 times a week for the last 6, 7 years. And our students all work this way, our postdocs work this way. We have quite a vigorous remote interconnected network. So a little bit of background about why we thought this was important to do. And all of us are involved with climate change, ocean and the oceans. That was a beautiful picture from Ted Blanco. This is a very iconic picture from the NASA website showing the global temperature is going up. And you're all aware of that. So I can skip this slide right on over to, although there's a pattern, I should show, yes, there's a pattern. And if you're on the website, you can move that bouncing ball around and see how the temperature has changed. There's a lot of attention right now on this cold spot in the North Atlantic. For the Southern Ocean, of course, we're working down here where it's more muted, but there is a signal, there's a distribution of cooler to the south and more warmth a little bit north of the ACC. It's blotchy in that picture. We'll see some better pictures in a bit. This is a graph from the IPCC AR5. That was now we're in AR6. AR5 showing that 93% of all the excess energy in the Earth system is in the ocean. And this is showing its progression with time with some error bars on it. And what we like to point out is that the ocean absorbs most of that energy. The atmosphere is this little purple thing down at the bottom. Of course, its heat capacity is very different from water, so that makes a big temperature change. And the ocean is taking up most of the heat, both in the deep ocean, the blue wedge, and the upper ocean. And we've mapped that out, and there are continuous versions of these maps showing where the heat is going in the upper ocean, which is kind of overall. The North Atlantic is a really big player. The Kuroshio is a big player. You see some really interesting structure in the Agulhas. When you look at the deep ocean, actually the Southern Ocean wins for sequestering the heat. And this is one of our motivations for saying, wow, this is actually a big player in the climate system, the Southern Ocean. And models have been especially poor at representing processes there, certainly back in 2012 and 13, where we're putting the project together. And one of the reasons is lack of observations. And so we proposed a program to head off to the Southern Ocean. This was part of the motivation. This is a picture from Perkey and Johnson, Sarah Perkey and Greg Johnson. And Sarah Perkey is currently a PI, a team member for GO-BGC. Just want to point that out. There have also been variations in ice sheets. This again from the NASA site showing, and you all know this, the Greenland ice mass is going down, and Antarctica, well, it's sort of bumbling along. We're going, oh, it's not changing very much. It started to plummet, and it's going down too. So of course we care a lot about understanding the whole system. The ocean's an important part of the system. And what it's driven by is one of the main drivers is the change in CO2. This is the iconic Keeling curve from Mauna Loa Observatory, up with some seasonal variations. And if you take that trend out, you see other things like El Nino, but basically the increase due to anthropogenic basically fossil fuel burning. So the ocean's a big part of that cycle of how the carbon goes in and where it goes. There's the curve. This is getting more towards what we're measuring. On the left is the air-sea carbon flux. So we want to know basically how does the ocean participate in the carbon cycle. And this is a map by Peter Landschutzer et al. The earlier ones are Takahashi et al. This is showing in blue places where the ocean takes up CO2, and in red places where it outgasses. There are big signals in the tropics and so forth in their structure, but the focus for today is the Southern Ocean from the subtropics on south to Antarctica. And here you see a pattern of uptake in the subtropics and then some hints of outgassing farther south. We're going to actually focus on that as one of our initial key results from SOCCOM, is quantifying that outgassing signal. On the right, you see the change in anthropogenic CO2 from Nikki Gruber et al. This is the latest product showing where the ocean's carbon, where the ocean is taking the carbon out of the atmosphere, basically. This is both a matter of taking up more carbon or outgassing less carbon. And there's a really strong pattern here too. We aren't at a point yet of assessing that from SOCCOM, but this is definitely a big focus of the next few years, we're starting to have enough data to really address this pattern. And another big change that's important for the ocean is that if CO2 goes into the ocean, which is a huge service to the climate, it affects the ocean. So this is a map of pH change from Zhang et al. 2019. It's kind of mapped. And one of the things we wanted to point out in motivating SOCCOM, the Southern Ocean Carbon Climate Observations and Modeling, is that prior to our measurements, which started in 2014, there were precisely 2 measurements of pH in the winter in the Southern Ocean. And now we have, I don't know how many tens of thousands of observations. So one of the things we're measuring directly is pH. Another part of the whole climate system is the productivity. This is just a map of satellite chlorophyll and a seasonal cycle with the area of variability. And we have instruments on these floats that we're out there with, and people working on understanding the productivity, mainly the seasonal cycle from the floats that we have, but that'll feed into looking at change. So that's the climate intro, and I'm sure all of you have have those slides yourselves if you're giving a talk that has to do with climate. Why do we want to go to the Southern Ocean? And why did NSF give us $20 million plus an additional 15 to continue the program to go there? So this is just a basic intro to the Southern Ocean. This is the GFDL-CM 2.6 model surface velocity from a number of years ago. This run was done a while ago, but we just want to point out, as you well know, that there's a circumpolar current system. It is not a zonally average ring around Antarctica. It has shape to it. It has eddies. Your eye is really drawn to the eddies. I'm a larger scale oceanographer, so I'm kind of interested in these standing patterns. Here's the Campbell Plateau and the Malvinas over here. Here comes the Agulhas down in the Agulhas return current joining the ACC. So we see actually a fair amount of zonal structure. We refer to that as zonal asymmetry. It's just that it's not a perfect ring. If we look at the role of the Southern Ocean, that's the looking at it from the top. Look at its role in the overturning circulation for the globe. This is a version. It's a very, very schematic of Antarctica joining all 3 oceans, the Atlantic, Indian, and Pacific together. In the Antarctic, we form an Antarctic bottom water, goes down. It's through brine rejection, through sea ice formation. Very cold water gets some more salt in it, sinks. And then that comes out and fills the bottoms of all the oceans. That's that direct connection that is the reason that the Southern Ocean is so, deep ocean is so sensitive. It has a lot of heat content change. There's pretty much a direct pathway from the surface down What's been happening over the last decades is that there's been less of that. And so the deep ocean has been warming. Basically, we have a lower supply of Antarctic bottom water. Out it goes and into all of the oceans. The other big overturning circulation that you're very well aware of is in the Atlantic meridional overturning circulation. Here it is, warm water in from the south, sinking in the north, and then coming back. And where does it reach the surface? Where does it complete its circuit? A lot of it completes it in the Southern Ocean, comes up. Antarctic bottom water going out into the Indian and Pacific and into the Atlantic also rises. There is a heat source in the tropics in lower latitudes, diffusing heat down that helps that get part way up. But a lot of it comes all the way back to the Southern Ocean. It's pulled up to the surface by the wind stress curl. And the complications due to open passage around Antarctica, the Southern Ocean dynamics that basically requires the return flow to come up as deep water. So it's all come up in the Southern Ocean. Why is that important? Deep waters are really old, especially in the Pacific and Indian. These don't have local sources of upper ocean water. Indian and Pacific, these are old waters. When water's old, getting up to several hundred, 500 years old, it starts to, well, it builds up nutrients and it builds up carbon, carbon being part of the nutrients. Part of what we want to focus on in SOCCOM is these deep waters bringing carbon up. And when you bring carbon up to the surface and it reaches, needs to equilibrate with the atmosphere, it can outgas. So I'm going to keep coming back to this outgas signal. The Atlantic is doing its own cycle over here. The North Atlantic deep water is a much newer deep water. It's only 200 years old when it reaches the surface, but it still has a buildup of carbon in it. So all these things coming up are going to bring carbon up to the surface. So that's basically a schematic of the system that we're operating in. So how do we get funded? We motivated it back, this is back in 2012, writing the proposal, that we have a major role for the Southern Ocean in taking up excess heat from the atmosphere, taking up excess carbon dioxide that's in the atmosphere, and supplying nutrients. And this was a paper by Jorge Sarmiento in 2004, nutrients that fertilize 3/4 of production north of 30 south. Just to go back to the schematic, that's when this water comes up with its high nutrients. A lot of it stays at the surface. Instead of turning into bottom water, it gets pushed north by Ekman transport and shoved into the thermoclines of the subtropical gyres. And that's going to supply that productivity. So that's an important part of the path as well. So the Southern Ocean is really important. It's a big role in each of these things, and yet we had very few measurements and almost nothing in the winter, and certainly nothing under the sea ice, which is a big part of the Antarctic. So that's motivation. Here's a map from Remick et al., basically using Argo observations for the last couple decades, showing the change in upper ocean heat content. And here you see Southern Ocean, in oranges is where the Southern Ocean is taking up heat. There's some blues that maybe have to do with, they do have to do with salinity. There's some heat uptake in the north, but basically they concluded that the Southern Ocean writ large, you go, oh, wait a minute, that's the subtropics, that's not sea ice. Well, so yes, the subtropical gyres are taking up a lot of heat in the Southern Hemisphere. And that's one of the things we'll be expanding on here with some slides. Actually, I'll expand on it right now. This is work from our PhD student, Ray Shi, Jiarui Shi. I'm co-advising him with Shangping Xie at Scripps. And he's submitted this paper to Nature Climate Change, just showing the heat content change from different observational products. If you know Shangping's work, you'll know that most of what Ray is working on is actually modeling. But in the last couple papers and what he's presenting now, he's been looking at Argo observations and observational products to validate the models and compare with them. Here you see heat going in, and I just want to focus actually on the smoothest one. This is the World Ocean Atlas. The heat is not going in uniformly all over the Southern Ocean. We have better pattern now from Argo and from these products than in the Remick et al. And there's some interesting patterns that show zonal asymmetry and maybe some cooling as well as heating. So again, it's sort of subtropical. So why are we focused on the sea ice region? Well, because it has a lot to do with other parts of the process. For instance, ice sheet mass loss and ocean temperatures. This is from Eric Vigneault, showing that when you look at ice sheet mass loss, it's not uniform all over Antarctica. There's some regions that are losing a lot more mass than others. This area, the Amundsen Sea and the West Antarctic Peninsula are huge, big projects going out there. Also, East Antarctica is losing mass, and other places are just not happening. That has to do with the ocean circulation and the prevailing winds, but the ocean circulation is really key, and that's shown over here, where you see the warm water at 300 meters, basically all along these coastlines. Cold water inshore of these subpolar gyres in the Weddell and Ross Seas. So warm water coming up and then coming up more strongly is actually a major factor in these melt-offs. So we want to get the circulation, we want to get the temperature distribution of the ocean, and we want to do it with observations to make sure that the models are doing this properly. So this is motivation for going in under the ice. And there's the sea ice system, the Antarctic, basically a very, very, very large area of seasonal sea ice in the winter, and then melting way back in the summer. This makes it really useful for doing profiling floats because a lot of the year they're under the ice melts back, and then we can get all the data back from the floats in the summertime. It also makes it risky. So we lose more floats than classic Argo does farther out, but that's just part of the risk. And we want to make sure we're measuring under the ice, getting the temperature distribution, the circulation, and the carbon, oxygen, and nutrients under the ice. Well, I did show this one already, but here we go. I'm going to show you some results that we have. This is the Landschutzer map of outgassing in red and uptake in blue. This is after our 5 or 6 years of floats. This is from another graduate student at Scripps, Channing Prend, working with Allison Gray, who's now at UW. She was a postdoc in SOCCOM, Sarah Gilly, Alex Halman, Ken Johnson, Steve Reiser group. This was submitted to Nature Geosciences. It's under review. This was showing our carbon flux estimates from our float profiles. Every single profile, we take the data, what we're measuring, which I'll show you in great detail in 5 minutes, what we're measuring, and we can calculate a PCO2 at the surface. From that, we estimate it, look at the atmosphere, and then calculate a flux. So everything is here, including all the seasonality, and nothing is left out. This is all our profiles, and you're seeing in blue where the ocean is taking up carbon, and in red where it's outgassing. So we're starting to be able to map the whole this carbon flux process in the Southern Ocean. And you'll see some floats all the way down in the sea ice region. Most of these floats are in the ACC. Part of what Channing is focusing on is why there's more outgassing in the Indian and Pacific sectors than there is in the Atlantic sector. We wouldn't have been able to even ask that question before these floats. Here's the nutrient supply. This is a map from Jorge's paper in 2004. Basically look at the top map, which is an indicator of where nutrients are coming from. If they're blue, they came from the Southern Ocean. If they're orange, they're from North Pacific overturn. So you see most of the world is seeing a lot of Southern Ocean water. So our strategy for really understanding how the Southern Ocean works in climate change is three-pronged. One is our observations, so our building array of biogeochemical profiling floats. Second is state estimation, which is ingesting that data along with everything else that state estimates do, and producing a biogeochemical output. So this is called the Southern Ocean State Estimate. It's part of the ECHO consortium of state estimation models. And Ariane Verdi at Scripps built the biogeochemical adjuvant for the state estimate. So they have moved on. They're actually doing the same state estimation for a lot of areas like the tropical Pacific, the Indian Ocean, California current. They're branching out to lots of regions. This is the Southern Ocean state estimate. And then there's a large group of people working on analyzing coupled climate models and experiments. So over 10 years, over the years, we're supposed to, over 10 years, deploy 320 floats. We have so far, we're at year 6, 7, deployed about 205. We have a pandemic slowdown last year. We only deployed half of our floats due to lack of ships, unable to travel to foreign ports. These floats all carry pH, nitrate, oxygen, and bio-optical sensors. This is measuring fluorescence and backscatter, which are converted to chlorophyll and particulate organic carbon. We had the state estimate, B-SOSE, and then we're working on coupled models. So here we are. We had been funded for 6 years. We got funding for the next 4. It'll be a total of 10. And our current phase is SOCCOM 2, and the main goal right now is maintaining what we have and desperately working on that with the last year. We can only build so many floats a year, so build and deploy. So we're going to deploy 35 to 50 this year coming up. I do this organization of the cruises. I have a long history working with shipboard measurements. And so we're organizing 4 to 6 cruises a year, which graduate students go on, postdocs go on if needed. If not needed, if the group of scientists at sea can handle all this for us, that's fine, that's great. So we pull in shipboard measurements along with these float deployments. So we have validation in situ data for the floats. Okay, what's in our observing system? You're probably mostly familiar with Argo. I'll just say very briefly what a profiling float does. Basically, it's sitting at the surface. It dives down to 1,000 meters, stays there for 9 days or so. Then it dives all the way down to 2,000, and then it profiles up to the surface. And this is where you get your main profile, temperature and salinity from Argo. And then it sits at the surface briefly to transmit all the data from that profile and get its location, and then sink back down again and do the cycle. So that's an Argo float. That this technology was actually invented in the WOSE project, World Ocean Circulation Experiment, in the 1990s, and it was invented at Scripps by Russ Davis. Argo is now a key observing system for the global ocean, and that's the distribution of floats this past November, showing all the countries involved. There are usually about 4,000 floats out there profiling every 10 days all over the world ocean. Back in November, a lot of these, the reason I'm showing a November map is, well, I don't know why, just am. Seeing a lot of what's going on in the Southern Ocean here. There aren't as many Argo far south, and if you looked at this map 5 years ago, Argo was limiting itself to being north of the ice. And so SOCCOM stepped in and said, we gotta have observations in the ice region. And moreover, we're gonna do biogeochemistry. So a lot of floats far to the south here are actually SOCCOM floats. SOCCOM data from the day 1 of the whole experiment were public. They're out there as part of the Argo data system. So we participate in the Argo data management. So we've added biogeochemistry. This is a cool schematic that was made for the program, showing the ships going along, dropping floats. The floats go up and down, and they report to satellites, and they get in under the ice. And there's our design for an Argo float with biogeochemical sensors. I already mentioned what we're measuring on them. We have just a little forest of things strapped on, and off they go. So there's 3 prongs to the biogeochemical Argo program now. There is an international biogeochemical Argo. It's now, Argo has reinvented over the last year to be calling itself One Argo. It includes the TS Argo, which has been going on. It includes biogeochemical, and it includes deep Argo. So Argo is now has a portion that's growing quickly. that's profiling top to bottom. The parts that I'm talking about are the biogeochemical. So there was an international framework. Ken Johnson and Hervé Closter are the co-chairs of that. SOCCOM we can consider now to be a large regional pilot program for going global, basically showing that the concept works and we have the instruments, we have the sensors. So there's a deployment just in December. I don't have time to show the video, but I can show it later. It's fun. You get to see the float go in, go off, and right itself and go down. And if somebody on the ship goes, oh, there it goes. So this is a deployment. No, I'm going to go on. So at present, the Biogeochemical Argo program looks like that. A whole lot of the Southern Ocean is due to SOCCOM. There are growing arrays in the north. Actually, many of the same groups are deploying floats in the tropical Pacific and off the coast here. China and India have big components. Europe and Canada are putting in a lot of oxygen floats in the North Atlantic. We are currently putting in floats in the Western North Atlantic from GO-BGC. So there's what we are. This is the existing program. This is the program that's going in. A big difference between SOCCOM and GO-BGC is that SOCCOM was funded with a full science program. It's organized around the science questions. How does the Southern Ocean participate in climate? Oh, we need observations to actually begin to address that. How GO-BGC is funded and how NOAA funds things and other countries will be funding things is saying, these are great measurements. Let's collect the measurements, and the measurements are all available, and there's no science funded. So what we were going to rely on is all of you and all of your colleagues to write proposals to get funding to analyze the data, which are all available within. Well, for biogeochemical, everything's available immediately as real-time data. Don't use it if it's biogeochemical. Wait till it's had an adjustment, which takes a month or two. So here's our deployment strategy for the next year or so. We're heading into the Southern Ocean, a few more cruises. Here's what we just deployed. Right now we're deploying here in the Western Atlantic. This Japanese line is probably canceled due to pandemic. We were really hoping to get North Pacific this summer, but we probably won't. But we're heading out. So there's a float out there in its cardboard box. In that case, the deployment, it just goes over the side, the box melts off, and the float is free and goes down in profiles. Here's our data set. If you're absolutely totally welcome to use it. It's public. It's through the Argo GDAC. If you want additional products, which include all the estimates of the carbon parameters, come to our website and find our data sets, and you can get them. You can get DIC and PCO2 and alkalinity. You can get chlorophyll and POC. You can go to ERDAP and find the same product if you're more used to using that. Yeah, we have a bunch of publications on how we do this. Biogeochemical sensors, that is Ken's main thing, developing nitrate sensor and the pH sensor. MBARI is all of the funding from Packard over the years, very important. So there's some papers on the sensor performance, and we continue to, that is a continuous evolution. And then we have to take what we measure and turn it into a carbonate system. And so there was a lot of work right at the beginning of SOCCOM, and that continues. I'll call out Nancy Williams working with Laurie Juranic at Oregon State and Dick Feely at NOAA PMEL. And then now we're mainly using work from Brendan Carter, also NOAA PMEL, and Dick Feely and so forth, who have come up with empirical algorithms for estimating alkalinity, pH, and nitrate from the floats. So this is a really important part of our system. We also, work on sort of observing system design. Where are you gonna, we're starting from scratch. Where do we put the floats? My answer is usually, well, where's the ship to deploy a float from? But once you've got a ship, it's going from Cape Town to Antarctica, where do you want to put your floats? How many floats do you want to put in? So it's really important to have an eye on oceanographic regimes. and also an eye on dispersion of floats. And so these are two parts of what we're working on. And SOCCOM also, and this is Isa Russo, many of her photographs are in here, has used a machine learning technique to classify Argo profiles. This is the TS profiles, and then we can use those to help decide, where to put biogeochemical floats. There's a lot of work on that by others as well. And then this is from another graduate student at Scripps who's done a transition matrix approach to using trajectories to project where floats will go. And this is a tool that's available, PDF. If you put a float in, there's a little Argo float going in the water, and you click on it, this is where it'll show up. It could show up in PDF land. Here's our biogeochemical state estimate. Matt Maslow and Ariane Verdi, who are really the only group producing these large-scale ocean, sea, ice biogeochemical state estimates. And this is being then extended to other groups. This is Joellen Russell with modeling. On SOCCOM's site, you'll find metrics for the Southern Ocean. And then she's been working with postdocs and graduate students on some really exciting results on freshwater forcing of the Southern Ocean. There is a climate model atlas. And we have an outreach program, which is called Adopt a Float. And if you have a school, a favorite school, or a favorite teacher or somebody you know who might be interested in adopting a float, we're going to be looking for teachers in classrooms. So far, a whole lot of our floats are adopted. Schools send their name of their float. They get to choose the name. They send what they want, artwork on there. Some graduate student or other gets pens and decorates the float for them, and we do interaction with the teacher and with the classrooms as the floats go in and as the data come back. So this is a fun thing. And we also have an ROV challenge coming up and workshops for educators. So some results. I need to just see what time it is. I can't tell from this WebEx. Sorry, I'm going to lean over. Can't see where I'm at. I have 5 minutes. So we have a lot of publications. We have a lot of results. I'm going to focus on the carbon flux result. We have this sort of zonally average picture of how the Southern Ocean works, and it's got a lot of complexity in it as is. This is based on many different people's schematics. We have some ice, we have some winds, we have waters coming in, coming up, splitting, going down as the Antarctic bottom water, or going out at the surface in the Ekman layer. The ACC threading through that. The regions of carbon release, where we have upwelled high carbon waters, and regions of uptake through the biological solubility pumps. So this is all there. And we have the schematic that I already went through, and we have the air-sea carbon fluxes that I already went through. We have outgassing and uptake. So one of the questions we had was, well, sure, that's fine. That's a zonally average view. Where's it really happening? Can we see the circulation that's actually bringing the carbon up that's outgassing? And so this is some work with, this is a PhD at Scripps, Veronica Tamzit. This is a paper by Heidi Chen, who's a postdoc at Princeton. First of all, over here, you see in the spokes of the wheel, Atlantic, Indian, Pacific, here's basically the carbon potential for what will outgas. And you see a lot of carbon in the Pacific, a lot of carbon in the Indian, even some carbon in the Atlantic, rising in these little chimneys, but it's happening all the way around Antarctica. This is from hydrographic data. So this is the water that's going to come up. And then we have this very low carbon water in the subtropics. What Veronica did was to take and group with Adele Morrison at Princeton, and undergraduate student, then Henri Drake, who's now a graduate student at MIT, did particle release experiments to look at the pathways of these deep waters to the sea surface in the Southern Ocean. So I'll show a slide of that. So the pathways are spiraling. They come out of these oceans. The water moves up and around as it comes up and reaches the surface. So that's been an interesting voyage to look at how that works. And then we have this map that I showed from Channing Prend of where the outgassing happens. I'm just going to skip quickly. I've said that. This is a little video showing Veronica's particle release. This is actually in the CM 2.6. They did this in 3 different models, and they all come, basically the results that are accepted and published that we really rely on were the same in all 3 models. So in the state estimate, CM 2.6 and CESM. So releasing particles in the deep water, only following ones that go all the way to the surface and never go back or down or south north. Then she mapped this out for all 3 oceans. And this happens to be a video for the Indian, but there's an there's an Atlantic and Pacific video too. And there's the spiral coming in. You could do it from hydrographic data. This is from WOS data. And around it comes, and the warm water reaches the surface near the Antarctic Peninsula, and that's where the ice is melting. So we're going, oh, well, it has something to do with heat. This pathway of warm, carbon-rich deep waters to the sea surface matters not just for carbon, but for heat. And I'll skip on. This is another slide from Veronica's work showing how that upwelling happens. It doesn't happen in a nice, neat spiral. If you look down deep at 1,000 meters and look at where water's actually upwelling, most of it is at eddy hotspots at topography, where the ACC crosses really complicated stuff. Makes a lot of eddies, and you have much more potential for waters to move up or down, but we're only tracking the ones that go up. Those eddy hotspots are essential for ratcheting the water up to the surface. Then it reaches the surface in a pretty broad distribution. This we really think is accurate because all the models do this. Where the water reaches the surface is model dependent, and that's going to depend on the surface model physics. And that's important to know that there's work to be done on how to connect subsurface waters to the sea surface. This was the first work on carbon outgassing from Allison Gray, her postdoc at Princeton, using the first couple years of floats that we had out there with annual cycles. And here's her graph of showing how the carbon fluxes work. Subtropical region, there's a lot of uptake. So these negative bars, the color bars are her estimates. The gray bars are estimates from prior work, Takahashi and GCB 17. Subantarctic zone, similar, although weaker. Polar frontal zone, now we're seeing some differences in sign, but the error bars are kind of, overlapping. And then we get into the southern half of the ACC where isopycnals really reach the sea surface. And here the outgassing signal from the floats was entirely different from the climatologies. Why? We think mainly because we didn't have data for the climatologies. And so we're seeing a much larger outgassing signal than climatologies had suggested. So this was the new major result. And Channing has continued to follow that up and shown that a lot of that connection is happening in the Indian and Pacific Oceans, and it's through an entrainment process. How it actually gets to the surface is an abduction process. How does the water below the mixed layer get entrained into the mixed layer and stay at the surface? And it happens in these regions. I won't dwell on it, but that's paper that's submitted. Let's see, what should I do next? That's our outgassing. That's our sort of the kernel of what we're doing, but we're interested in a lot of other stuff. And so we have 130 publications by a lot of different people who are really interested in a lot of different things in the Southern Ocean. Just want to show just a little hint of what we're doing with some of it. First is how the sea ice impacts the overturning circulation. This is Ryan Abernathy and a few years ago. Second is just curious topographic features, Taylor columns that are very important in the Southern Ocean for mixing water up to the surface. Oops, that shouldn't say widespread, but widespread supercooling. And then we'll return to that signal of heating. How does the Southern Ocean heat? This is from Ryan. He took the Southern Ocean state estimate, which I've introduced, and looked at this upwelling branches of, here comes the circumpolar deep water coming up to the surface and splitting. And what he showed is that when it comes up to the surface, this upper limb of the overturning circulation, this is forming thermocline water. that water comes up at a higher density than the thermocline. How does it join the thermocline? It has to get less dense. Well, we were all thinking that it had to do with heating. The water comes up and heats. Well, it does heat a little bit, but what he showed was the main input of buoyancy is the sea ice melt at the outer edge of the ice zone. And so here are the maps that really show this. In green is where the water is gaining buoyancy. It's getting less dense because of the sea ice melt. And in magenta is where it's getting more dense because of sea ice formation. So you get a fractionation, essentially, of density. You get much higher densities close to Antarctica. There's a constant flux of sea ice out. It doesn't mean that the ice from here melts out there, but on average, there's more ice production close to Antarctica and more ice melt out at this ring of the ACC fronts. And so you're going to put in a lot of fresh water out here. So fresh water matters a lot for the Southern Ocean overturning. That upper limb, water rising and staying in the surface and moving out into the thermoclines, relies essentially on that fresh water input. I want to say it loud and strong. It has to be in the models. It has to be right. This is a second little, just little regional projects, which are some climate impacts, have major impacts on productivity in the Southern Ocean and on things like decadal variability here over in the Weddell. Over here is chlorophyll. In October, there's an early bloom in this region of the Scotia Sea. It just seems really kind of arcane, but actually it points to some topographic features. We had some floats that got stuck on them. This is a Taylor column, and a Taylor column mixes water to the surface really nicely. So it's actually blooming here early because there's a source of iron to the surface. It's kind of fun. Over here, you might have heard more about, if you're interested in climate, this decadal phenomenon called the Maud Rise polynya. There's a topographic feature in the Weddell Sea. Back in the 70s, it opened into a very large polynya. A couple years ago, with our floats trapped on Maud Rise, it opened again, not because the floats were there, but it opened. And we were there to measure it. And so I'll just skip on. Here's the Maud Rise. Here's the polynya from that year. Here's the earlier polynya, which was much larger. But basically what we're finding is that the Maud Rise mixes warm water up to the surface, which preconditions it to be warmer. Every year, seasonally, this region opens up earlier than other parts of the Weddell. It's the first place to melt. But every now and then, every couple decades, it opens in the middle of the winter, late winter, and this particular one was tracked to very strong storms, cyclones that year. And then we also see blooms over that rise that are due to mixing of nutrients upward. So that's running out of time. I like it because physical oceanography. I'm a physical oceanographer. It's nice to see these things you learn in GFD or fluid mechanics that actually working in the ocean and mattering Taylor columns. This is another cool result. This is very recent in GRL. Alex Halman, who's a postdoc in the SOCCOM program at Princeton. We found one of these floats came up in the middle of Ocean Sciences meeting last year, and it had water that was too cold. And Ken Johnson, who's a biogeochemist, goes, "Is this right? Is there something wrong with our thermistors on this float?" And we go, no, that's supercooling. Well, what's supercooling? So Alex went at it and found all the observations, which included all the CTDs attached to all these guys' heads in the marine mammal program. So there's hundreds of thousands of dives of these guys, plus our Argo floats out there, and he mapped where supercooling happens. And this is a process that may not be represented in models very well either, but it's very prevalent. So it actually does matter to how the water changes its density. So he found incidences of supercooling in sea ice regions in all these areas, and then supercooling that's due to the ice shells themselves, the subice cavities around Antarctica. So it's a nice paper. And then I want to return finally to the heat uptake in the Southern Ocean. This is not biogeochemistry, but it's part of the SOCCOM work, and it should relate pretty closely to that anthropogenic carbon uptake when we get to it. So this is from Reishi. Again, looking at, he's showing that overall, there's warming in the Southern Ocean. Warming happens, this is his only average picture of the temperature trend from Argo, from south to 30 south, so from Antarctica up to 30 south. There's the ACC contours of velocity, and you can see where it's warming from Argo on the north side of the current. There's the current core, his only average current core, warming on the north side of it. There is a sea level trend that goes with that from a VSO satellite altimetry. So there's an increasing, this is a trend, so it's an increasing gradient of sea level across the current, which means it's accelerating. So you can look at find an acceleration of the ACC, zonal average ACC, over these decades. And that zonal acceleration is happening on a poleward shifted from the center of the ACC. It's a new finding. The Argo data set is now long enough to start to look at trends rather than just decadal variability. And it had been basically concluded before that we weren't seeing much acceleration. What Ray is showing is it's there, and that the acceleration is coming from the buoyancy distribution, that there's a lot more warm water on the north side, and it's not warming much on the south side. And that's what's driving the acceleration and the poleward shift. It's not a wind forcing. So that's an important finding. The reason there's an asymmetry in warming, that it's cooler on the south side and warmer on the north, was a nice paper by Kyle Armour and John Marshall a few years ago, that we have the upwelling circumpolar deep waters, which put the brakes on the changes here. It's constantly moving cool water to the surface, and that stabilizes it here. But over here in the subtropics, you can push heat in. You're at the surface, you're constantly in contact with the atmosphere. And this is a picture, another, I'll just skip on here. There's regional dependence to that pattern. So what we're doing now is heading out globally. Argo is there, of course. Argo has filled the global basins and slowly moving into the Arctic and moving into the deep ocean. And we're now moving into global biogeochemistry, looking at that carbon, oxygen, and nutrient over the globe. So that's it. And it didn't stop for anything. Have any questions?
Thanks, Professor Talley. If anyone has any questions, they can ask them in the chat if they don't have a microphone, or they can raise their hand. If you expand the attendee panel, there's like a little hand icon, so you can click that. We do have 2 text questions that people have been waiting. The first is from Xiaomi Liu. They ask, I'm interested in B-SOSE 50 meter per mile CHL chlorine. I'm struggling. C estimation. Chlorophyll. Oh, I got it. Is this chlorophyll data available to public now? Is this chlorophyll estimation compared with ocean color results in Southern Ocean?
Yes. First of all, the measurements are all available, and they're continuously available. So as profiles come in, the data are available, and the output from B-SOSE from the state estimate is all public and available. And so I'm happy to send you the link for that. Yes, people are working on that, but there's definitely room to get in there. Channing Prend, who I mentioned, looking at the carbon flux, has been looking at chlorophyll, mainly from satellites, and then in the European models, the NEMO model, he's he's doing a little fellowship in Paris right now. So looking at controls on chlorophyll interannual variability. So B-SOSE is available. Matt Masloff is always open for business. Anybody wants to ask him questions, anything about SOSE, it's available.
Thank you. And if you have any links to share, we can always use the event site for that. So anybody interested in that should definitely check that out. We have another text question from Trevor Clack. They want to know, have you ever heard of the project Vesta? If so, do you have any opinions about it?
I haven't, so tell me about it.
Trevor, if you want to unmute yourself, I can give you a platform so we can talk about it. In the meantime, we have a question from Ron Vogel. He asks, the uncertainty in ocean heat content has decreased over time. Is that due to more observations, or is that more to the uncertainty than that? Is there more to the uncertainty than that?
It's more observations, yeah. So when you have really sparse ship observations, you have fair weather bias and you have a shipping lane bias. And so the uncertainties went way down once Argo was pretty much global. And that's, yeah, it's measurements. So how well can you map sparse data? And there's lots of techniques for doing that. Yeah.
Thank you. Trevor also said I could unmute him, so you're unmuted.
Oh, hello. Can you hear me? Am I muted now?
Yeah,
Okay.
you're muted.
Thank you. Sorry, I wasn't prepped to come up with this, so on the spot, let me prep with a little bit of history for some people. The late Ordovician period is usually held up as this time where there was a really high carbon dioxide concentration, and then we had a relatively low solar output at that time, which I think accounted for the fact that during that time the Earth's temperature was not as hot. But of course, going forward, now that the solar output has increased, I think by another 4%. If the CO2 concentration was very high, it would, the temperature would be quite hot. So obviously we had to draw down that carbon somehow. And I think the current explanation is that the Appalachian Mountains were pushed up, and then that allowed for a lot of silicates to be weathered and draw down the carbon. So, all right. So in a sense, in a similar way, I think Project Vesta seeks to mimic something like that. It's like a way to draw down carbon by, I believe the rock that they're trying to study is using some sort of volcanic olivine and putting them on beaches so that you can use the wave energy to sort of break them down and then allow it to, in the same sense, draw down carbon from the atmosphere. I don't know. So I don't know if you've heard of this, or but you said you haven't. So I don't know if you have any opinions, just your first impressions about such a solution.
No impressions. My husband, that would be up his alley. Jeff Severinghouse, he's really he does paleo, and interested in all of these engineering solutions. I know nothing, so I'm sorry.
No problem. All right, thank you.
Yeah.
Thank you, Trevor. Does anyone else have any questions? That's it for my queue, but you can still raise your hand, or you could even chat me and tell me to unmute you. Okay, in that case, I think there's no questions. Well, thank you, Professor Talley, for giving us this great talk, and to everyone else, thanks for coming, and please come back next week as our seminar series continues. Thank you.